the introduction. My talk would be a bit more applied than the previous ones, and I will talk about the predicting bending moments of slender structures. And this problem basically comes from the industry. As you know, I believe, Norway has a bit of oil. So the oil companies, they would like to assess the wear of their structures which rise the oil from the seabed. And so a more general formulation of this is how do we predict the fatigue of slender structures. In this work we considered two of them. This is a very simple Euler Bernoull beam which is clamped on the sides, and a drilling riser which is used in offshore oil rigs. So basically we use this is a beginning of our work in this topic, and we use quite simple models which are adapted from several other more general frameworks like Seymour-Eisner model, Kirchhoff-Love model, nonlinear and linear Euler Bernoull descriptions, and Timoshenko beam, and others. And usually these structures involve description which is based on the direct product of the Euclidean space and the SO3 group for rotations, or some authors propose to describe these structures in special Euclidean group in 3 dimensions. So more specifically, we want to predict the bending of such structures because it is one of the easiest measures to assess the wear of the structure and to understand when this structure should be replaced to avoid accidents. So our main limitation in this work is that we can use, and the companies can use, only few sensors, and so we would like to use so much information as possible from the problem itself to minimize the number of the sensors. So our first simple model is to check the idea is the Euler Bernoull beam. It is governed by this fourth order equation. It is clamped, it is a horizontal beam, and it is clamped on the sides, where W is the displacement of the beam in the transverse direction, and Q is some external load. Basically, for this simple problem, we also expect that a simple machine learning model would be able to predict the fatigue in an adequate way. So our beam is of unit length, and we do not possess really relevant real-world data. We just generate it randomly. So we take several randomly chosen points of application of the force on the beam, and then generate random forces at these points, and then we can interpolate the values to get a continuous approximation to the load, and in such a way we generate our training set for this case. And the second derivative of the deflection would give us the target, which is the bending. So in this case, our machine learning model is very simple. It's just a linear regression, and the equation itself is linear. We expect that everything should be fine, and we, in this case, consider two options. So we can put one sensor or on the beam somewhere, or we can put two sensors and compare how the performance changes in this case. Also, we might expect that due to some symmetry in this problem, the predictions wouldn't change a lot depending whether we put the sensor on the left or on the right, or whether we put the sensors, two sensors, somewhere in between. So for example, in the first line of the table, we can see that the linear regression is quite a good method in this case, and we explain it as because we can see this result because the problem is rather simple, but we can still improve a bit by adding a second sensor, but the improvement is not so significant, but the accuracy of the prediction is 96%. So now we can go to the more advanced and interesting model, which is the drilling riser. So this is, in our setup, we also use a simplified model of oil rig. So we assume that the seabed is completely flat. So we assume the oil rig itself is fixed on the surface of the sea and doesn't move. And the riser itself, which is a very long and slender structure, can rotate and can deflect, and its upper and lower point are fixed. And for the oil companies, it is very important to predict the fatigue of the riser at the seabed, where it is connected to the head well of the mine. Yeah. So, and the riser equation is governed by this partial differential. The riser motion is governed by this partial differential equation, where we have, which excludes the stiffness, the tension of the riser, its linear density, damping constant, and some external forces that, in our case, model the eddy waves. Once again, they are used in case when the seabed is flat. The only important thing we discard in our model is so-called vortex-induced vibrations, and we discard them because they make the model significantly more complex and requires solution in 3 dimensions. So in this work we limit ourselves just to 2 dimensions, but these vortex-induced vibrations are also a very important topic in research in engineering, because they introduce quite a lot of damage to the riser itself. And once again, from the economic considerations, we would like to put 1 or 2 sensors on the riser in such places that they can be easily maintained and replaced if necessary. So in this case, we will have 2 setups. We will have only 1 sensor, similar to the Bernoulli beam. We can put it on the very top of the riser or somewhere below the sea surface in the water. And we can also economically use 2 sensors if one of them measures acceleration of the riser in the sea, and the other one is put on the top, on the very top of the riser. And we will compare how these 2 setups are. So as we expect that the external forces are somewhat periodic or quasi-periodic interaction, so we, for this reason, we use the so-called recursive neural networks. In this case, we decided to select one of the recent proposals, which looks like this, and it's called anti-symmetric recurrent neural network, and the authors of this model claim it has a better stability property than previous models. And we use this model because we want to assess the damage to the riser depending on the last n moments of time. So to this end, we have a moving window. We solve the riser equations using the finite element methods, and we generate data set which shows us the last 50 displacements and accelerations of the riser. And we compare how different machine learning models can predict the bending at the wellhead using 1 and 2 sensors placed in different places. Here we can see in the first table in the first table, we can see that compared with the Euler Bernoull beam, the linear regression, which is the first line, doesn't give a reliable prediction when we place the sensors in a convenient for maintenance places. That is at the top of the riser. This is the 10 meters below the sea surface. However, when we use a more advanced model that can use more information from the physical system itself, we can see a significant improvements when the sensor is put on the very top. But it should be noted that if we can put sensor on the near the head well, the results are quite close, and it is also an more or less expected result, because we can more or less surely say that the bending itself is maximal at the connection point to the well. On the other hand, if we can use two sensors, one put on the top, which is just inclination of the riser, and the other sensor is somewhere in the water measuring the acceleration, we can see that after certain depths we note an improvement in the prediction. So for this engineering problem, like engineering related problem, we can see that more advanced models work better, and well, as expected, the more sensors you have, the more information and better prediction you can generate. But unfortunately, the companies do not really want to do this thing because it's more costly. It's costlier to maintain such systems. So to sum up, in our work we show that so we really can predict the fatigue of engineering structures. And the things that we see important to proceed with are the following. First of all, in the best case scenario, it would be great to work with real data. Unfortunately, companies are not really willing to give out this data, although they have it. They are ready to sell it. But probably with some collaboration between the university and the industry, we can finally get this and try our simple models, which are also fast to predict, on the real data. Meantime, the thing we can do is to improve our simulations. Here it was also worth mentioning that there basically exists quite developed software for such a problem, for simulating the oil rig risers, but it's also not an open source software. It's also kind of has limited availability. And the final question, and the most interesting for us to proceed, is how the geometric properties of the problem can be used. Because we just approached this topic, and we know that, for example, the manifolds which are used for description of the problems, but how can we use them? So, and at the moment there are two approaches already existing in different spheres of geometric machine learning. The first one is the direction proposed by Jeffrey Hinton and his collaborators and people from Amsterdam's university, is basically to construct convolution-like networks, but instead of the image convolution, these first neural net layers are supposed to extract some Lie group features depending on what Lie group underlies the problem. The second approach is similar to this one, convolutional one, but it takes a bit a different direction. They try to learn also Lie group invariance through some different techniques, and this, for example, is used for movement recognition. A similar talk was given several similar talks were given early in the morning about the movement recognition, and they used signatures for this, but as the existing literature on Lie group movement recognition claims that it's possible also to work with Lie groups using neural networks, and will be interesting also to compare how these two techniques correspond to each other. And that's all. Thank you for attention.
Thank you.